Hopefully it could follow the proof, but really the goal is that you can work with these endpoint equations. It's very cool that we can use physics to describe something wobbling back and forth. We can get its time period, we can get where it is at split seconds, how fast it's going at different positions, its maximum speed. It'd be awesome if you could follow the proofs, but really just need to be able to sort of plug and chug as we work through using the equations. So for a question like this, the first part is what's its maximum speed? Our maximum speed equation came from conservation of energy. Maximum speed is root k over m, multiplied by amplitude. That's a little bit messy. For this one, now it's just plug and chug. Our k was 24. Our m we have to put in kilograms is 0.4, so square root of that. And multiply that by the amplitude, which was 0.15 meters. Chug it out. I'm getting a maximum speed of 1.16. Our time period equation, we got that from that crazy reference circle projection work. Time period is 2 pi root m over k. As may be expected, there's no amplitude in it. Time period doesn't depend on the amplitude, it just depends on the properties of whatever's vibrating, the m and the k in this case. The m was 0.4 and our k was 24. Again, just kind of a plug and chug. This one works out that our time period is 0. I'll give 2 decimals, 0.81 seconds. The third one is where people sometimes run into trouble. If I ask for a speed at a position, it'd be ugly to use those trig equations. You could, but you'd have to do it twice. A better method is to use conservation of energy. When something wobbles back and forth, we know that all the joules are spring potential when it's at amplitude. And when it's at the equilibrium, all the joules are kinetic. When we're somewhere in the middle, it's got a little bit of each. It's got some spring potential and some kinetic. The halves are going to cancel. For this particular question, we knew the amplitude was 15 centimeters and the k was 24. We're curious about 5 centimeters. So the k was 24. The amplitude was 0.15 when we're in meters. The k was 24. We're curious about what's happening when it's 0.05 centimeters away, or 0.05 meters. The m was 0.4. Oops. So from conservation of energy, all the joules were spring potential at an amplitude, but at this partway position, it's got a little bit of each. If we do some subtraction, we can clean it up first, but subtract the ks squared over to the other side. We can do a little bit of algebra and figure out how fast it's going. The number I got when I did it was 1.09. It's close to its equilibrium position, so I'm not surprised that it's going almost the maximum speed. The closer it gets to equilibrium, the faster it goes. Our last question asks, part 4, what is its position after 4 seconds? Whenever a question asks for something about a specific time, for those, use the tricky trig equations. I'm calling them tricky trig because you have to be in radians on your calculator. This is the only time in the whole course where it matters, but you have to be in radians for this equation to work. Based on the derivation, we used the definition of radians, or we used the way we use the projection. The trig will only work when we're in radians. This particular question asks for where it was. So our equation is x equals a cos omega times the particular time. We figured out the time period, so we could use that version of omega, but based on the numbers given in the question, we know k and m were given. It would be smarter to use that version. So really x is equal to a cos root k over m times delta t. Now it's a plug and chug. You can go back and look at the question. The amplitude is 0.15 multiplied by the cosine of, under the square root sign, our k was 24, our mass was 0.4. Outside of the square root, the question's asking what's happening after 4 seconds. So I have to multiply by 4. crunch all that out. You have to be in radians before you hit the cosine button. When I crunched it out, I got an answer of 0.14. It's positive, so that means it's whichever way we pulled it to begin with. Let's say to the right, it's 0.14, which is smaller than the amplitude, which is good. It's not very much smaller, so it's basically, smaller than the amplitude, so it's basically back at the amplitude position after 4 seconds. That's how we work simple harmonic motion equations. You don't necessarily need to have the proof memorized. Well, definitely don't have to memorize the proof. You just have to